Hello, this is the High Pro Factory Side Chat, and today we have a special guest joining us, our lab manager, Curt Martin. Curt, if you could introduce yourself and tell a little bit about how long you've been here and what you do.
Yep. So I've been with HiPro for 16 years now. As you mentioned, I am the lab manager here at the Anderson facility. I oversee the oil analysis program that we run, and then also the operations of our DFE test bench. And I also do some time with the engineering department doing application engineering.
Wow, that's great. That's great. So today we're going to focus on a lot of what you do, and I think it's going to be very informative for the people watching this chat or listening to it on the podcast. So let's start with particle sizes. In general, what size particles do you focus on in the lab and when you're running testing?
Yeah, so when we're running testing, typically what we're looking at is the 4 to 40 micron channels. In the field, we do deal with particle sizes that are smaller and larger than the 4 to 40 range. But typically in our research development, oil analysis, that's primarily what we're focusing on, 4 to 40 micron.
Okay, well, mentioning that being 40 micron is the largest size that we have in focus, and we know that that is basically all those particles are smaller than what we can see with an unaided eye. How do you measure the concentration of particles in the oil?
So typically what we do is we'll use a laser particle counter that will tell us the particles per milliliter based on a micron range or a particular size. Or we could also run a patch test where we take an oil sample, run it through a 1.2 micron patch, and then we'll analyze that patch under a microscope. And at that point, you have to manually count the particles.
So for the patch test, where we have a filter, 1.2 micron filter that we draw the oil through, and it captures the particles that are larger. What are some of the advantages of using the patch test kit?
So with the patch test kit, you can visually see the particles. So in some cases, you can use a reference guide, or with a trained eye, you can tell what type of contamination is in the fluid. For example, shiny wear metals, they're easy to identify. So that's one of the good advantages with the patch test is you could actually see the particles, try to identify what they are. And it's a good reference tool that you could use in the field where you get a quick reference for what's going on with your system. You don't have to pull a bottle sample, send it to a lab, and then wait a couple days or a week to get results back. You could use the kit and do it there on site and have a good understanding of what's going on with your fluid in the matter of minutes.
It sounds like that would be good for the field because not many customers have laser particle counters, but it seems like almost all customers will collect oil in a bottle sample on site, and I guess that would be convenient then.
Yeah, it's very convenient. It's a much cheaper option versus a particle counter. So that is a good tool to use as a reference. It's quick, it's easy, and it's fairly inexpensive.
So it's quick. I like that. So let's go to the laser particle counter. That one is a little bit more accurate. Can you tell us about the advantages of that and when you typically would use the laser counter?
So yeah, typically, like you mentioned, it is more accurate than manually counting particles on a patch with your eye. So we would use that in a lab setting, although there are models that are portable. You could take them out into the field. You could connect to an oil sampling port and do an online particle count. That's best case scenario because you're not relying on somebody to pull a sample out of a sample port, make sure the port is flushed correctly, the bottle samples are clean. So the particle counters are more diverse. They give you more accurate reading, and they can be used both in a lab setting and in the field if needed.
So in your lab test stand, you have laser counters, and then we have a portable one that you utilize as well for bottle sampling. I would assume they can be used online as well.
Correct, yes.
Okay. So when you use this laser counter, is there a certain ISO standard that we use to quantify the quantity or the concentration of particles in the oil?
Yeah, so it's based on the ISO 4406 standard. So what that is if you look that standard up, there's a table, and it basically gives you a range of particles per milliliter. And depending on the number of particles per milliliter, that will correlate to an ISO code. So for an example, an ISO code of 10 has a volume of 5 to 10 particles per milliliter in that range. And then if you go up to the next ISO code, which would be 11, you basically double your counts per milliliter.
Okay, so there's two aspects to the 4406. It's what I'm hearing is you have your ISO codes, and then you also have your actual particle counts. And each code, as you move up one code, it doubles or potentially can double in size. So when you look at your lab reports, what do you focus on and why?
So when you're looking at a lab report, most lab reports will report the ISO code, but then they'll also report the particles per milliliter. And the particle per milliliter is going to give you more information than just the ISO code. What you could do is you could look at the number of particles per milliliter and you could determine where you fall within that range. If you're on the low side or the high side of the specific ISO code number itself. So you may have two oil samples that have the same ISO code on the 4 channel, but you could potentially have twice as many particles in one sample versus the other.
So that brings up a couple questions. One of them is, you said the 4 channel. What are the channels that we'd like to focus on as far as the lab report?
The 4 micron, 6 micron, and 14 micron. Those are the 3 channels that make up your ISO code.
Okay, and the 4 micron channel, that would include all the 6 and 14, and then the 6 would include the 14 as well?
That's correct. Yeah, so it's 4 micron, so it's greater than equal to 4 micron. And then for the 6 micron, it's 6 greater than equal to 6 micron. 14 micron, it's greater than equal to 14 micron.
Okay, and one of the things I like to mention at this point is whenever we look at the ISO codes, you mentioned there is a potential to have a doubling of the number. Let's pick on the ISO codes of 10 and 11 again, 10 being 5 to 10 particles per milliliter, and the ISO code of 11 being 10 to 20. So you look at the actual particle counts to see if we're close or not. What I like to mention at this point is the ISO codes themselves are a limit, not a target. We used to, many, many years ago, call it a target, but we realized, and it's not just HiPro, but the international community realized that this is a hard limit. So a target is something to achieve, a limit is something to avoid. And so we do use it as a limit. That's how we say it. That's how we preach it. So looking at the particle counts, you can actually tell, okay, if I'm at, let's say, 12 particles per milliliter, I'm close to the limit, even though I'm above it, versus if I'm at 20, literally double the limit.
That's correct.
Okay, so now that we've established what particles that we like to focus on, 4 to 40 in size, and now we know that the ISO code chart, the 4406 chart, is what we use, and that's an international language, so we can speak to anybody anywhere around the world, and it's the same language. Now I'd like to talk about testing the filter elements for efficiencies. There's several different testings that you do. I know 2 of them are ISO standards. Can we walk through those, starting with ISO 16889, and kind of progress from there as far as what is required of you in the lab, and why we do those tests?
Yeah, so the ISO 16889, it's a steady flow test, meaning when you start the test, you set your flow rate and it never changes throughout the entire length of the test. So let's say you're running a test at 30 GPM, it's going to run at 30 GPM from start to finish. That was the industry standard, the 16889. And what ISO likes to do is they like to develop standards that are repeatable. That's the main goal, is to develop a test method that can be repeated from one lab to the next, from one filter to the next, and you should, in theory, get comparable results. So that's what's been used as the industry standard up to this point. Back about a month ago, June of 2021, they've released a new ISO standard. That's the ISO 23369 test method, where it's ran like the 16889, but the primary difference is it's a cyclic flow test, meaning that the flow will change flow rates throughout the cycle of the test. And what they did here is they wanted to get a test that's a little bit more representative of real world conditions. In a hydraulic system, obviously you're going to have flow rate changes and pressure changes and whatnot. So this test will get you one step closer to a real world scenario, but yet it's still a repeatable test from one lab to the next.
Okay, so if we go back to 16889, before ISO 23369 was adopted, and we've been talking about that for years, but about 25 years ago, we stumbled on some information that we learned from filter elements, and that led us down a path to do some extensive testing. Can you tell us a little bit about that testing that we do?
Yeah. So the testing we do is called DFE testing, meaning dynamic filter efficiency. And like you mentioned, about 25 years ago, we realized and understood that the 16889 test was not mimicking real world conditions. So we wanted to test our filters as close to a real world environment as we possibly could in a lab setting and see how they basically performed versus a steady flow test. And what we found was when you start to change the flow rates and you get this dynamic flow cycle, the elements will start to shed particles. So with that information, we then started to develop the DFE test, and it became our primary research and development tool that we now use to develop new medias, improve our assembly and processes in the manufacturing area to make a better filter that reduces the risk of shedding particles. Every element's going to shed particles during a dynamic flow cycle. It's just a matter of how many particles it does shed. And with the DFE test, we've been able to pinpoint these unloading events and then develop a strategy and an engineering goal to develop our medias and our elements so that it reduces that risk.
Okay, so with the dynamic filter efficiency test, in doing that, we separate the filter element conditions into the 4 different conditions that it's going to experience in real world, which is low flow steady state, low to high flow increasing flow rate, high flow steady state, and then decreasing from high flow to low flow. So those 4 we break apart individually. Do you feel like that gives us a more information to be able to determine where the element weaknesses are and able to improve on it, and just in general?
Yeah. So the way that we collect the data throughout the course of the DFE test is it's a real-time data collection. So we're able to see during these flow rate changes what's going on with the element. We're able to collect that data, pinpoint these unloading events, see how severe they may or may not be. And then, like you said, at the end of the test, we break it all down into those different flow parameters. So we could see how the element tested only under the high flow cycles versus only the low flow cycles. And then we can also look at those flow rate changes and see when those unloading events occur. We can see how severe those clouds of dust are coming out of the element, and then we can make modifications to our pleat packs, our medias, our production techniques, and then make a better element to reduce the risk of that happening. Where with the ISO 23369 test method, you don't get the real-time data collection. You're pulling particle counts, but the way that they're spaced out, it's not able to pinpoint these flow rate changes and see what's happening during those flow rate changes. You get more of a averaged or a normalized value.
Okay, so to give credit to 23369 is a significant improvement over 16889. However, what it sounds like is multiple samples are pulled during the DFE test during each condition, whereas with the 23369, you're changing flow rate so rapidly that you can't break those different conditions down, and so you take less samples. It may not be as informative. Is that accurate to say?
That's correct.
It is repeatable, and it is an advantage over 16889. So there are some advantages to it. It's just we take it to another level with DFE.
That's correct.
Then we take it to another level, and let's talk about cold start retention. Can you tell us about why we actually do a cold start retention test, what's involved, and what we learn from that?
Yeah, so the cold start retention test is basically a worst case scenario. It takes an element at the end of its service life, and then we basically hit that element with a zero flow to a full flow cycle, and then we measure the cloud of dust coming out of that element. And the reason we do that is we know that elements aren't always changed when they should be out in the field. Due to maintenance schedules, staffing issues, whatever it may be, elements do run in a system longer than they should. And we want to protect our customers' critical components, even in worst case scenarios. So we run this test to see how severe the clouds are coming out of not only our elements, but also our competitors' elements. And like I said, we're the only company doing a test such as this, so we can collect that data and reduce the risk of that happening with the hypermedias.
Because ultimately, like you said, worst case scenario, the element is full of contamination. If for any reason there's a flow change that occurs, there will be an unloading event. If we can manage that unloading event and keep the worst case scenario under the limit, good. If not, then you could potentially have that event push your contamination levels above the limit.
That's correct.
Okay. All right. That's good to know. So just to summarize on cold start retention, I have customers that say, well, that does not apply to me because I don't change flow rates, like a lubricating oil system or a filter card or a kidney loop. Can you explain why that may not be the case?
Yeah, so every system is going to experience a dynamic flow cycle at some point in time. If it's either, the equipment doesn't run 24/7, so they stop it at the end of a shift and then come back and restart it at the beginning of the next shift, there's going to be a dynamic flow cycle that takes place from the starting and stopping of the unit. Same thing if a piece of equipment goes down for maintenance or unexpected repair work needs to be done. You're going to have to shut the system down and restart it. So you're going to see dynamic flow cycles no matter what type of system it is. Even on a filter cart that runs at a steady flow rate, while it's operating, you shut the system down, turn it back on, there's going to be a dynamic flow cycle.
One other thing I like to mention to the customer as well is if you are going to shut your system down for any reason, whether it's maintenance or to shut down the facility for a period of time, go home for the night, if you know that the filter element has reached its end of life, but it hasn't yet indicated, it's a good opportunity to go ahead and change that filter element instead of waiting a few more days for indication, so you can avoid that cloud of dust that, even though we manage it, we still would like to proactively manage the cloud of dust and eliminate that if possible.
Yeah, that's a good idea. Change those elements out before you restart the system. And like you said, avoid that potential cloud of dust coming downstream and damaging critical components.
We've already caught the particles. Go ahead and remove the filter element instead of unloading and have to recapture them in the future.
Yeah.
Okay. And then one last thing I would like to ask about is other lab tests that you do in your lab. Like, for example, Carl Fisher or MPC. You do water testing, and tell us a little bit about that and when you would perform the water test.
Yeah. So water testing is our most common oil analysis in the lab. So typically, most oil samples we run in our lab, we're going to do 3 tests on it. We're going to do water content, ISO code, and MPC. Those are the 3 most popular oil analysis we run. So the way that we do it is, if we get an oil sample where we can see free water floating in the bottom of the bottle, at that point we know that there's a large amount of water in this oil sample. We're not going to run that sample through a laser particle counter because you're going to get a false reading. The laser particle counter is going to count the water droplets as particles and you'll get a false high reading. So what we'll do in situations such as that is we'll run the water test, so that way we know the ppm content of the fluid, and then we will run that oil sample through a patch test instead of a laser particle counter, because the patch test isn't affected by the water content.
Okay, so let's say you don't see free water at the bottom of the bottle, but it's enough to mess up the laser counter. What are indications, looking at the printing of the ISO codes, that would indicate that it could be aeration or could be water contamination?
Yeah, so if you see ISO codes that are either the same digit across all 3 codes, or maybe the 4 and the 6 channel are showing the same codes, then you look at the individual particle counts and they're all very close together, and most of the channels are very high. That's a really good indication that you have either air, water, sometimes even varnish in the fluid.
Okay. All right. That's good. And then you mentioned MPC. Why do we run the membrane patch colorimetric test?
So MPC testing is looking for the varnish potential of the fluid. So we typically run these on turbine fluids, EHC system fluids, phosphate ester, then also some AW fluids. And the reason we want to look at that is varnish can cause a lot of problems obviously within the system, but then varnish can also, like I mentioned earlier, affect your ISO code test results. So it's a soft contamination that will go in and out of solution. And if it has fallen out of solution and you run that through the particle counter will detect that varnish within the fluid and give you a false high reading there.
But MPC is so accurate that we don't rely on just visual inspection of the oil color to determine if it's varnish or not. Is that correct?
That's correct. It's not uncommon to get a oil sample that is black in color, but have a low MPC test. And then vice versa. It's not uncommon to get a oil sample that is crystal clear in color and test high on MPC. So visual inspection of the oil alone, you can't depend on that to gauge the varnish potential of an oil. You need to run the MPC test.
Well, that's great information. I think that's really good. Thank you for your time, Curt. This has been very informative. I think the people that watch this chat or listen to the podcast are really going to learn a lot from that. So thank you. This has been the High Pro Factory Side Chat.